الآن أوكي.
Okay. So just to elaborate from the beginning, I mean, this video is from Watson, and basically it describes how future manufacturing facilities will look like. So at the beginning, the video starts by saying that there is a blizzard expected, and what would the management decide to do for that, how to reschedule the production lines. And then the supercomputer will do the computations and evaluate like which production line will produce faster and how much downtime we can mitigate. Then another predictive maintenance alert will predict that according to vibration and temperature readings, X machine will fail within 24 hours and give the decision for the management to decide which production line you want to put down based on the predictive maintenance alert. Then after that, we should have some technology that can be able to predict the failure by just using the augmented or virtual reality techniques. And then the technician will go and attend the problem, and the according to the big data repository that the supercomputer have, the machine learning will ask for feedback. So basically, it's now asking for supervised learning. After sending the feedback to Watson, the feedback will be compared with the knowledge or the learned in the model. And then after the comparison and after extracting few features, Watson will find the root cause analysis. And the root cause analysis turns out to be that the humidity after being exposed to humidity, it will fail in X and Y hours. And this is the important part that I will focus on. Now, after gathering data from all sensors, forming an IoT and streaming this data into the supercomputer, now all the data from different sensors will be compared to the model that is stored in the cloud. And IBM Watson will predict that there will be no outages based on the data received from different sensors for the coming 30 days. I know that we are still far from there, but let's go through the presentation and show that most of the technologies that will help us to get to this level are proved, at least in research state. And I know that they're available also in the market, but they're still in development phase. So let's now talk about Industry 4.0. So now we're living the era of Industry 4.0. And we started with the first industrial revolution when steam engines were invented, and then the second industrial revolution when manufacturing entered the mass production era. And then after that, we have the automation that kicked in. So there is minimal human interaction. PLCs and DCS have the logic to carry out the control, SCADA systems, etc. And now we're in the era of cyber-physical systems. So in my presentation, and actually this is where I'm specialized in, I'll focus on system integration, machinery, big data, and network of sensors and machines. And I'll focus the example and the case study that I'm going to present basically talks about vibration monitoring. So we'll start from vibration monitoring for big machines, how to do feature extraction, how it was done traditionally, and what is the approach using deep learning, and how to estimate the remaining useful life for different machines. So before that, I will talk about internet evolution. So before the introduction of the internet, humans used to communicate with each other. Then the internet came, where we have emails and entertainment. People could communicate with each other using the emails. And then it came that we have e-commerce, e-production. And then after that, we have Internet of People, social media, Skype, Facebook and YouTube, and now we're in the era of machine to machine. Now we are talking about machines speaking with each other. We have infinite number of sensors, smart sensors that are connected to the same network. So now machines can talk to each other. So our current platform, according to Forbes, there is, for a normal size plant, 1 terabyte of production data is created daily by the average factory, but less than 1% of that is actually being analyzed by manufacturers. So this data is really important. I know that there are huge historian servers currently that store the data, but if you look in depth actually into the utilization of the data content, it's really minimal. And this data is really of a great importance. So let's now talk about ANSI and ISA 95 reference models. So I believe most of you are aware of this models. If you talk, this is actually valid for both process industry and for also, discrete manufacturing. If you look into the physical production process level 0, the numbers here different based on different references. There is a physical production process, and then on top of that, we have sensors, actuators, and robots that monitors the first level or level 0. Then those sensors will stream data into monitoring systems, DCS, PLC, etc., of the control systems. On top of operation management, and the upper level, we have business planning management. So this is the current, model that's been there for a while, for decades, and it's working perfect. But if you notice that the lack of interconnection, for example, if the sensor generates different number of alarms, then that's going to be sent to monitoring systems, DCS, and if the operator or the operation engineer in the morning receives 100 or 200 or 300 of alarms, he will just, there are different techniques for alarm rationalization, know what is really important, what is really not important. And some of them might be, referring to a real problem, and others might be referring to just an incipient problem, the problem that is still evolving, but due to the rush of the manufacturing, life, some of the errors might be overlooked. So the interconnection between different layers is not fully autonomous nowadays, and those alarms need to be refined before sending to upper level management. When you talk about upper level management, they do not care about the number of alarms. All what they care about is how far or for how long I'll be able to produce. Whether we have 1 alarm or we have 1,000 alarm, how far am I able to be functional and be able to produce? And this is the key. Now, deep learning can actually automate the interconnection between those levels, as we're gonna see in a few slides. So smart manufacturing basically says, or defined according to the Leadership Council, smart manufacturing enable information about manufacturing process to be available when it's needed, where it is needed, and in the form that it is needed. And this is what we mentioned before. I want the data, I will just get the cream out of that data. As a top level management, I don't want to see that I have today 100 alarms. The form that I want to understand or textualize this data is in the form that I'm gonna be able to work for 24 hours before shutdown. And this is what basically smart manufacturing is about. So when we talk about system integration now, the integration between lower level all the way to the upper level, we know that there is big data generated at bottom level. And as we go up, big data, if it is analyzed efficiently, will lead to big knowledge. And when it comes to people at decision-making level, that will lead to big understanding. So let's see now, this is the problem or the case study of vibration monitoring. So for basically vibration signal or vibration in machines can be a result of so many reasons. Can be a result of misalignment, can be a result of some failures or unbalance. But the signals usually that we receive in real time are usually transformed into frequency domain or looked at the signal from different angle. So the traditional approach of how machine health monitoring was done is that we log the data and we either send the portable spectrogram to the field, or if we have advanced system one techniques. So if the sampling rate is at the right frequency, we have defect frequencies, the fastest frequency and the lowest frequency. And if the sampling rate is according to the Nyquist criterion, then we'll be able to detect those peaks. But imagine if we have, if you are monitoring the vibration over a complete lifetime of a machine, and for example, if we have a frequency of 100, then if we, for example, doing the test in the lab, let's not talk now about industry, but in the lab level, we're going to end up with really big data set. And by just looking into the data, but just presenting it on the screen without any processing, we want to be able to extract any useful information. So the current techniques now of that process engineers use to set lower and higher control limits, and if the either the vibration or temperature exceeds those limits, we send an alarm. Currently, also people are doing data-driven health monitoring. So data-driven health monitoring, basically what it looks like is that the data scientists build manual and predictive models. So the data scientists will look into the data stored in the historian, and there are multiple features that can be extracted from the data. And what do I mean by features? For example, if you have vibration data for 10 seconds, so instead of having the data in, for example, 1,000 or 2,000 cells, you can extract discriminative features. You can look into the peak-to-peak, for example, or the root mean square, or the kurtosis, or the frequency content from the data. So data scientists can go in depth and extract useful feature out of the data and build predictive models based on that. But the main downside for this approach, for the data-driven, is that, I mean, it's not practical, first of all, to have data scientists, working in each and every plant. And we actually need more than one data scientist, basically, because imagine the number of turbines and compressors available, for example, in one Aramco or SABIC refineries or affiliates. So this is the current approach, which is the data-driven. The input usually is analyzed by a data scientist, and then after that, the models are extracted. And part of the knowledge required here is a data analytics knowledge, how to reduce dimensionality instead of having 1,000 by 1,000 by 1,000 matrix. How do I reduce the data, but so that I do not compromise the data content, but at the same time, I can look into that data instead of dealing with huge numbers and matrices. So this is the time where big data analytics is very useful. We know that if you have data for vibration data for 1,000 hours, we know that there is a micro patterns that are hidden in terabytes of data. So by just visual inspection of the data, you won't be able to detect those micro patterns. But big data analytics has the power, or has the potential at least, to extract those micro patterns. So now, instead of looking into the traditional approach by just setting lower and upper control limits, we'll be able to look in depth. For example, this is an anomaly detection, and this is a micro pattern that is detected in terabytes of data. Big data analytics has proved, has been, employed in language processing and biometrics and in so many other fields, and it has proven its performance. So when it comes now to data analytics, so basically we are looking into deep learning feature extraction. And what I mean by automatic feature extraction, as I mentioned before, data-driven approaches now basically utilizes the knowledge of data scientists to do classification and develop the inputs. For example, we have a car, you have some information about the car. Data scientists analyze this data to extract some features and then design the classifier. Deep learning will get rid of the data scientists. I mean, this is very optimistic, I know as of now, but now models are being developed. People are doing a really good job into embed actually the knowledge or the fusion of scientists' knowledge into deep learning, and deep learning can automate the pipeline. It can it can read the data, extract useful features, and design the classifier of the about the different problems. So as I mentioned before, features now are learned automatically by transforming data into abstract representation. And then we can, after extracting useful information from the data, we can either predict the remaining useful life of the machine. We can predict when this alarm is gonna appear, and that's all data driven. And if the classification or if the feature extraction is done properly, then that should be all automated. But as I mentioned before, we're still now in development phase, but the results, at least in the lab, are very promising. So let me give you a brief background about deep learning. So basically that...
Your time is, you don't have time. Please, and if you can conclude.
Yeah, I can wrap up in a few minutes. So basically, deep learning was first tested on biometrics. For example, if you have different pictures for the same person and different postures, so deep learning can actually extract the abstract representation of those pictures. So basically, you're looking at ghosts. So if you're talking about vibration signal, in computers, basically deal with pictures or vibration or temperature signal the same way. So we can learn abstract representation. There are different networks available. I don't know if you're interested, but if you want to, for your research, if you want to do some research about that, there are, autoencoders, convolutional neural networks that can actually do some type of filtering and then data compression. And once you compress the data, those features will show up, and then the accuracy of the compression basically is dependent on reconstruction of the original data. So I will show with you a few results of one of my papers. Actually, this is one of the data sets that are available online, where actually 12 faults were introduced into different bearings. So we have now 12 faults corresponding to different data set. So, and we have big data set actually that we were able to cluster the data, utilizing deep neural networks. So basically, this is a type that is called unsupervised learning. So you input data for 12 classes, and then after training, you see what's the output. So the only supervised thing here is that we color different clusters. And as you can see here, using different neural network structures, the network was able to discriminate different features from each other. So again, back to the pipeline, after you do the feature extraction, then you can project and find the remaining useful life, because this is now, we closed the pipeline starting from data acquisition to feature extraction, and finally by remaining useful life prediction. So the future research outlook, as I can see right now, people are working on raw data pre-processing. That data is contaminated with noise and other especially if you guys are all in the industry and you know those problems. People now are working on model selection. So if we consider, for example, image processing, now Google has a model that is published online that is trained on over 1 million picture. So people now are targeting to use those models for machinery, and because the more data that you show the model, the more the model is going to be robust and will be able to detect different anomalies from different machine. And one of the important things is incremental or transfer learning. For example, if you have 10 compressors in the plant, I mean, in different locations, so one model actually can be trained incrementally, starting from compressor 1 to compressor 10, so that you do not miss because even if different machines are manufactured the same based on operating condition and many other things, the performance and the remaining useful life also is different. So that brings me to the end of my presentation.